Analyzing concurrent programs is a complex task, and to alleviate this complexity, we are aiming to analyze the concurrent programs component in a component-wise fashion. That means we want to look at one thread at a time. In previous approaches that have attempted a local analysis on concurrent, the attention was focused on log-based programs mostly. In this work, we are aiming to be able to tackle all sorts of implementations, including non-blocking algorithms that do not rely on logs. On last year's CSF symposium, a similar work had been presented that was based on the Rely Guarantee framework to do so, but the analysis was conducted forward, and a closer look at the framework revealed that it leads to a fairly complex analysis. To mitigate this problem, we want to conduct the analysis backwards now. Our motivating applications are cross-domain components, which are designed to connect components of various security domains in such a way that no information can leak from a trusted component to an untrusted one. Imagine a scenario where you have a trusted writer that wants to communicate information with some readers, some of which are trusted and some of them are untrusted. This is done so via a shared buffer, a multi-purpose buffer which can hold public as well as secret data. The trusted reader can read both, whereas the untrusted reader should only have access to public data. Imagine this is for efficiency reason implemented via a non-blocking algorithm that does not use logs, but instead relies on a variable z, which allows us to alter the security classification of the buffer. If z is assigned to 1, we can rely on the fact that it's secret, and we can write our secret into the shared buffer X, but before we reset z, we need to flush the buffer, need to take out the secret data. We refer to Z as a control variable. It allows us to alter the security classification of the buffer. If we analyze this code, or want to analyze this sequential piece of code, we define proof obligations that guarantee us information flow security, and we define these proof obligations per instruction. If we do this analysis with respect to any other threads that are run concurrently, like the reader, we have to take into account how their effects on shared variables. In this example, obviously the buffer is shared, the reader has read-in access to this buffer, but also the control variable Z is shared because it's here used as a synchronizing variable, because the reader is implemented such that if it manages to update Z to 2, it can read. It cannot read if Z is 0 or 1. Since this piece of code of the concurrent set can be rather long, not as short as it is here, it is very tedious to take the whole code into account between each line of code that we want to analyze when analyzing the writer. So we want to work with an abstraction, with a summary of what the reader is doing, what the effect might be. In this case, this is the rely condition we are working with, and in this case it's as simple as saying the reader does not update the buffer, and it only updates the variable Z if it's not 1. In return, the writer has to provide a guarantee, we have to prove that the writer gives us a guarantee that is strong enough for what other threads rely on. So to prove this, that the environment does not break the proof obligations we have to define for each line of code, we define a predicate that we call stable R, and we say a predicate, like the proof obligation here, is stable under the environment, or under R, if When it holds initially and the environment does one or more steps, here abstracted by R, then it still holds afterwards. And this is saying that the environment does not break our proof obligations. What does the proof obligations look like that give us or that guarantee information flow security? Assume we have a lattice of security values where true symbolizes low and false high. In this case, we assume it's Boolean. It can be any kind of lattice, doesn't have to be Boolean. Then we can define a security classification, L, for each variable. And in order to be able to model value-dependent security classifications, like in our example, this maps variables to predicates. For example, the security classification of our buffer X is specified as Z is not equal 1. So Z is low if X is, the buffer is low if Z is equal 0 or 2. We also define the security level of the data held currently in the variable gamma. And in other approaches, gamma is defined as a type. In our approach, we define it as an auxiliary program variable that is carried through. So that means our analysis is purely logic. It's not a combination of logic and type system. This gamma can be lifted to the security level of whole expressions. So a proof obligation here, for example, for an assignment looks like this. I chose this assignment for an example. If the updated variable is a global variable, we have to make sure that the security classification of that global variable is strong enough to hold the security level of the expression we update to it. If furthermore the updated variable is a control variable, we have to make sure that the effects of this update on the controlled variables are not detrimental. So we have a predicate that we define secure update such that for all controlled variables, the security classification of these controlled variables after the update is strong enough, still strong enough to hold their data. In this case, either the buffer was already holding low data or the buffer's classification was already low. It's not falling from high to low. If we to conduct this analysis backwards, we make use of the weakest precondition predicate transformer, WP. WP of an instruction C to reach a postcondition Q defines all states for which instruction C results in states specified by Q. We extend this to a predicate transformer that we termed WPI if, that just conjoins the weakest precondition for our instruction to reach Q with the proof obligation of that instruction. If we conduct this analysis, we're starting at the back and apply WPI if over each instruction backwards to the top. So we start with true and reason over the last instruction, and which results in the proof obligation of the last instruction, because the weakest precondition of any instruction to reach true is just true. In the next step, we compute the weakest precondition over the second last instruction that delivers us, that results in states that satisfy this proof obligation. This is this WP, this proof obligation feeds into this. And we conjoin it with the proof obligation of the second last instruction. We feed this further upwards to the beginning of the code, at which point we have to prove that the initial state, P0, is strong enough to satisfy the predicate that was pushed upwards. If we do the same analysis for concurrent programs, we furthermore have to also check if each instruction satisfies the guarantee G, and also that the whole predicate gathered so far is stable under the rely condition. So what does it look like if we term the first conjunct as pre? Then the analysis looks like this. We apply WP, IF, RG over each instruction backwards. We have the blue part you've seen on the last slide, and we extend this blue part of the predicate with the guarantee and the chamber stable check. And that takes into account the effects of the environment. In conclusion, we have provided a very general framework based on rely guarantee reasoning to analyze concurrent programs in a backwards fashion, and this backwards analysis leads to significantly simpler predicates for information flow security in particular. And that is because you only feed backwards information of the state that is needed for reasoning. In a forwards fashion, you have to push forward the whole state space. Our analysis is based on standard verification techniques, and hence we can tap into existing tool support. We have provided a soundness proof in Isabelle Hall and have extended these theories with some degree of automation via tactics. We have also built a custom-made analyzer which interfaces to an S&T solver. In future work, we want to apply this analysis to assembly code. Thank you for listening, and I will be available for questions.